Factors affecting equilibria means what conditions can change the equilibrium condition. Okay, so in most of the cases equilibrium condition will change and it will attain equilibrium again. Okay, so same equilibrium constant will be there except temperature will change the equilibrium constant itself, and these changes are governed by Le Chatelier's principle. What is Le Chatelier's principle? Before I tell you the definition, in the simplest form, it is if there is any change in the reaction, the system will try to, or the reaction will try to oppose it, to counteract it, means to nullify it. So if we increase the pressure, reaction will try to decrease it. If we increase the concentration of reactants, the reaction will try to decrease the concentration of reactants. If we try to increase the concentration of product, the reaction will try to decrease the concentration of products. If we remove the products, for example, okay, so if we try to decrease the concentration of products, the reaction will try to increase the concentration of products, always opposite of it. Okay, so how does it affect it? And that is something I will be talking about later on, but first the definition. Change in any of the factors that determine the equilibrium conditions of a system will cause the system to change in such a manner so as to reduce or to counteract the effect of the change. So in simple English, it is written that if we do any change to the reaction will oppose it. This is applicable to all physical and chemical equilibria. Now these are the factors I will be talking about one by one, which may, or in some cases may not affect at all. Okay, but we will discuss. Effect of concentration change, for example, we increase the concentration of products or reactants or decrease. Effect of pressure change. Effect of inert gas addition, if we add any non-reacting gas, inert gas or any non-reacting gas. Effect of temperature change and effect of catalyst. One by one. So the first one, concentration change. If we add or remove any product, then what will be the change? Suppose we have a reaction, and reaction is hydrogen and iodine combined to give you hydrogen iodide. Okay, all of these are gases. Now, as per Le Chatelier's principle, if we make any change in this reaction, it will try to oppose it. So suppose I increase the concentration of hydrogen. So this square bracket itself shows it is concentration I am talking about. So whenever we say this one, we don't need to write the word concentration. When we increase the concentration of hydrogen, the system will try to, reaction will try to reduce the concentration of hydrogen. How can it reduce? The only way to reduce the concentration is that the reaction goes in forward direction. It is possible if the reaction, when the reaction goes in forward direction, only that is the possibility that hydrogen concentration will decrease. It means it will shift the equilibrium towards right. So how do we say it? We say that the equilibrium is shifted towards right. Remember, equilibrium constant will not change. There will be some different amount of hydrogen concentration, iodine concentration and hydrogen iodide concentration at equilibrium, but the value of Kc will still be same. The value of Kp will still be same. So concentration change cannot make any difference in the equilibrium constant, because the reaction itself will manage the change in the concentration. So reaction will change in such a way that the reaction constant, that is equilibrium constant, remains same. Now understand it in a different way. Suppose I have here, okay, graphically, if we understand, try to understand the same thing. Okay, we are at equilibrium. Okay, so we are at equilibrium. Yeah, this is equilibrium. And at equilibrium, if we move with time, the concentrations will not change. So all these concentrations you see, these are constant. Concentration of hydrogen or iodine or hydrogen iodide at equilibrium are constant. But suppose at equilibrium, I increase the concentration of hydrogen. Remember, I'm not touching anything else. I'm saying just increase the concentration of hydrogen. What will happen? If I increase the concentration of hydrogen, to reduce the concentration of hydrogen, the reaction will go in forward direction. If reaction goes in forward direction, it means concentration of I2 will start decreasing because it will start getting consumed. So whatever concentration of iodine was there, it will start decreasing. So it decreases. It will get consumed. Hydrogen will also get consumed. So from its higher concentration position, first we increased it. Okay, sorry. First we increased it. And after that, it will start decreasing because hydrogen will get consumed because reaction is going in forward direction. But hydrogen iodide will be produced. So that's why from its equilibrium concentration, it will increase. It will start increasing. Then they will attain some other values of concentrations, again constant. So a new point of equilibrium will be achieved. Here equilibrium will be achieved. There will be different values of hydrogen concentration, iodine concentration, and hydrogen iodide concentration, but the value of Kc here and Kc here will be same. So the values of concentrations will change in such a manner that the equilibrium constant remains same. So here hydrogen is added. You can be asked to draw a graph for any change. Suppose it is asked that iodine is added, it will be similar. In that case, the graph will be, in that case, you increase the concentration of iodine, you will start from here and then it will start decreasing. Hydrogen will start decreasing right from here because hydrogen has not been increasing, has not been increased. Hydrogen iodide, however, in both cases will increase, whether you increase the amount of any reactant, hydrogen or iodine. Now, same question can be asked differently also. It can be asked that we remove the hydrogen iodide produced. Hydrogen iodide is removed. So instead of H2 added, you will write Hi removed. Okay, so let me explain it separately. This is the diagram. You have H2, I2, Hi. Okay, here you have some constant concentration, obviously, because this is the equilibrium we are talking about. This is constant, this is also constant. But at equilibrium, this is equilibrium, we removed Hi, some of the hydrogen iodide. If we removed hydrogen iodide, then what will happen? Initially, it will decrease. Okay, so you have decreased here. This is the case. Initially, it will decrease. Then what will happen? Because the reaction is H2 plus I2 gives you 2Hi. Again, the reaction will go in forward direction. Why? Because it will try to increase the concentration of Hi. You have reduced it, you have removed Hi. The reaction will try to produce it. So what will happen? From here, the Hi concentration will start increasing and will attain another constant value. Hydrogen iodide will get consumed because the reaction goes into forward direction. H2 will also get consumed because reaction is going in forward direction. So they will attain another equilibrium somewhere here. New equilibrium. Kc here and Kc here will remain same. This is an example. In this example, ferric ions, Fe3 plus ferric ions, which are yellow, okay, in aqueous solution, when they are reacted with thiocyanate ion, HCN is thiocyanate ion. Then they produce this complex, okay, this compound, which is deep red in color. This is deep red in color. Now what can happen if we change the concentration by adding something? Okay, so what we are doing first here, we add oxalic acid here. So what will happen? Oxalic acid actually will react with Fe3 plus. Oxalic acid reacts with ferric ions to produce another complex, this complex. It means the concentration of ferric ions will reduce because these will be consumed. If you add oxalic acid, these will consume some of the ferric ions. So it means the reaction will go in forward direction. It means the reaction will go in backward direction because the concentration of ferric ion will be reduced. System will try to increase this concentration. It will try to increase its concentration. It has to go in backward direction. So what will happen? The intensity of red color will decrease. Intensity of red color will decrease. So it will get converted to orange color because when you mix red and yellow, you get orange color. So it can be asked in exam that we get orange color. What could have happened? Okay, what will be the change in equilibrium constant? In which direction the reaction is going on? Okay. If we get intense deep color, it means it is going in forward direction. If we are getting something yellowish, okay, means orange, the reaction is in backward direction. So reaction goes in backward direction, the intensity of red color decreases or the orange color increases. Next example, same reaction, but now we add HgCl2, okay, mercuric chloride, HgCl2. What will happen? Mercuric chloride decreases red color again. Why? Because Hg2 plus will react with the thiocyanate ion. So in this case, in previous case, what happened? Oxalate reacted with iron ion. So oxalate ions reacted with ferric ion. Here from HgCl2, mercuric ion, Hg2 plus is mercuric ion. This will react with the thiocyanate ion to produce a complex. So again, the system will try to increase the concentration. This will get consumed by Hg2 plus. System will try to increase its concentration, will go in backward direction. Again, the red color will decrease. Next, we add potassium thiocyanate. We already have thiocyanate ions here. Potassium thiocyanate will also provide the same ions. So it means the system will try to decrease the concentration of HCN. So potassium thiocyanate means it will give you K plus and HCN minus ions. These ions and these ions means concentration of thiocyanate ions increased. System will try to decrease it. How will it decrease? It will go in forward direction. When it goes in forward direction, means deep red color intensity will increase. Now the effect of pressure. To understand the effect of pressure, first you need to understand how the pressure is caused. Pressure is caused by the number of molecules of a gas. Suppose you have this container. This is the container. You have very few molecules here. Say you have 1 mole. In 1 mole, you will have 6.022 into 10 power 23 molecules. The pressure is created because these molecules hit the walls. When they hit the walls, they produce some force. They exert force on the walls. That force by the molecules is actually the pressure. If instead of 1 mole, now suppose you have 2 moles, you have now many molecules. Okay, double the molecules. Now double the molecules will strike double the times on an average, so they will create more pressure. Okay, the possibility of striking the wall increases. It means the pressure is directly proportional to number of moles, and you know that from PV equals to nRT. Pressure is, you can write it as N RT by V. In this case, I'm taking same volume. Volume is constant, R is constant, T is constant. If all of these are constant, means pressure is directly proportional to the number of moles. It means if we increase the pressure, the system will try to decrease it. And how it can decrease? It can decrease if it can decrease the number of moles. Vice versa, if we decrease the pressure, the system will try to increase the pressure. How it can increase the pressure? If it can increase the number of moles, then it can increase the pressure. How it is applicable here? Understand it. Suppose you have reactants giving you products, and the condition is such that you don't have same number of moles on both sides. Suppose you have different type of reaction, in which case you have 2 moles here and 3 moles here. Suppose you have reaction PCl5 gives you PCl3 and Cl2. You have 1 mole here and you have 1 plus 1, total 2 moles here. Then in that case, if you increase the pressure, then system will try to go in that direction where it can reduce the pressure. It means if it goes in backward direction, 2 moles will be converted to 1 mole. It will reduce the pressure. So in this case, for this example, the reaction will go in backward direction, or you can say reverse direction. Okay, it won't have any impact if both reactants and products have same number of moles. So remember, the effect of pressure will be nil if both reactants and products have same number of gaseous moles. Gaseous moles only you will consider. In this case, PCl5, PCl3, Cl2, all are gases, so I have considered everything. So pressure change obtained by changing the volume can affect the yield of product in case of a gaseous reaction, where the total number of moles of gaseous reactants and total number of moles of gaseous products are different. Okay. So effect of pressure change on above reaction can be understood in 2 ways. Okay, how we can understand it? First is number of moles. How many number of moles we have here? 4. 1 plus 3 gaseous moles only, and here we have 2. So if we increase the pressure, this reaction will go in forward direction. The 2 ways. Okay, first one I have already explained. If you increase the pressure, the reaction will go in forward direction. We can understand it in a different manner also. If pressure is increased, system will try to balance the effect of change in concentrations also. How? Understand it. Okay. So for that, we know that QC is given by, for this reaction, it's given by products concentration divided by reactants concentration raised to their stoichiometric coefficient. Okay. It is 3 here. It should be 3 here. We have 3 moles. So to the power 3 here. Now in this case, suppose you increase the pressure, then what will happen? Okay, you increase the pressure, and we are talking about that volume is changing. So what will happen in that case? This is the initial volume. Okay, and at that time it will be Kc. It will be Kc at that time. Now suppose you decrease the volume by applying the pressure. You are applying pressure. When you apply the pressure, suppose this is a piston type of thing. If you apply pressure from here, piston will come here, and now the volume is half of it. So initially if I say the volume here was V, now I'm saying the volume is 0.5 V. If we increase the pressure, this is just for explanation, so I am taking some easy values. Or you can say, just to make it even easier, you can say it is initially 2V and then it is V, just to even avoid the decimals also. You can do that also. Now calculate the Kc and Qc. And you know, if Qc is less than Kc, reaction will go in forward direction. If Qc is greater than Kc, reaction will go in backward direction. So how do we calculate that? Forget about it. Kc will be CH4 concentration, okay? And what will be the CH4 concentration? It will be, suppose I initially write it as Kc, okay? Initially I write it as Kc. This is not Qc, say it is Kc. Then the concentration of methane will be its number of moles, say number of moles here, N1, N2, N3, N4. Okay, these are the number of moles at equilibrium. So what will be the concentration of methane? It will be N3 divided by V, number of moles divided by volume. H2O, it will be N4 divided by V. Carbon monoxide, it will be N1 divided by V. And hydrogen will be N2 divided by V. But here I will have to have cube here. We have 3 moles of hydrogen. Okay. So it means N2, 3 is the stoichiometric coefficient, N2 moles, N2 divided by V whole cube. Now calculate Qc. For Qc, we have 0.5 V. We don't have V. Now it is 0.5 V, but number of moles will remain same just when we have applied pressure. Just when we have applied pressure, okay, just in one step, very quickly, at that time, number of moles were same, N1, N2, N3, N4, but the volume became 0.5. So concentrations now will be, methane concentration will be its number of moles divided by 0.5 V. Volume is now 0.5. N4 divided by 0.5 V divided by N1 divided by 0.5 V and N2 divided by 0.5 V whole cube. Now understand it. What will happen here? Sorry. This 0.5 V, this 0.5 V, sorry. Don't cancel V, just calculate 0.0.5. Okay. Rest part we will compare with K. So this 0.5, this 0.5 will get cancelled. So what I will get N3 by V, and here I will get N4 by V, and then I am writing this 0.5 outside. 1 by 0.5, I am taking this outside. I am trying to get this one. Okay. Then it will be N1 divided by V, which I already have, and here it will be N2 by V whole cube, and 0.5 whole cube I am taking outside. So if I am taking it outside, it will be 0.125. 0.5 whole cube will be how much? 5 cube will be 125. 0.5 whole cube will be 0.125. So it means if I now do it, this part is Kc. This part is Kc. And then I have here 0.125 divided by 0.5. That is how much it is? It is 125 divided by 500. It is 125 divided by 500. And 125 divided by 500 will be 1 by 4. It means Qc is 1/4 of Kc. It means you get Qc is less than Kc. Kc is 4 times Qc. So Kc is greater, Qc is smaller. And if Qc is less than Kc, means reaction will go in forward direction. You know that. So this way also you can explain. In terms of concentration also you can explain. In terms of pressure also you can explain. It is important to understand that when we talk in terms of concentrations, we can apply it for non-gaseous form also. But if we are talking about in terms of pressure mole only, number of moles in terms of pressure also, In that case, it will be applicable for gases. So both ways possible. Whether you say it like this, that the reaction will go in that direction where the number of moles are reduced if you increase the pressure, okay, and vice versa. Or you say like this, in terms of concentration, you calculate QC. If QC is less than Kc, it will go in forward direction. If QC is greater than Kc, it will go in backward direction. So equilibrium will shift. How you will say? You will say equilibrium will shift in forward direction because reaction will go in forward direction. So QC is less than Kc. That's why the reaction will go in forward direction. Effect of inert gas addition. No change. Why no change? The reason is very simple. Because concentrations do not change. Suppose you have a container and here you have hydrogen concentration, iodine concentration and Hi concentration at equilibrium. Now suppose you have the same container and now you have some inert gas into it. You inject some additional gas, say that gas is argon. And there will be some concentration of argon also, but argon is non-reacting gas, it is inert gas. Is there any change in the concentration? No. Concentrations are still same because suppose you calculate the number of moles here or molarity here. Molarity here was number of moles of hydrogen divided by volume V. Both have V volume. Volume has not changed. Container has volume V. Now here you have not changed the number of moles. Number of moles hydrogen is still same. So here also it is number of moles of hydrogen divided by volume. So concentration of hydrogen has not changed. Similarly, concentration of iodine has not changed. Similarly, concentration of hydrogen iodide has not changed. So if nothing has changed, the value of QC, which will be Hi whole square divided by H2, just for example here, will be equal to Kc. Concentrations are same. So reaction will remain at equilibrium. Reaction does not change. However, if volume increases, then obviously the change will be decided by change in concentration, which is something I will explain with an example later on. Otherwise, if it is not mentioned, if it is simply asked, what is the effect of inert gas addition? You will say, no change. Equilibrium does not get disturbed. But if it is mentioned that volume increases, for example, a balloon, okay, balloon. You have a balloon and you have H2, I2 and Hi here, and there is some equilibrium. Now you inject some inert gas, so now it will increase the volume. If you increase the volume, concentration will change because concentration is number of moles divided by volume. So now concentrations will be decreasing. Volume has increased, concentration molarity will decrease. So obviously that will affect the equilibrium. Effect of temperature change. This is the only change which will change the equilibrium constant itself. Okay. To understand it, consider the heat. Heat produces temperature, you know, right? You have to provide heat to increase the temperature, or to decrease the temperature, you have to take the heat out of it. Consider heat as one of the components. Means if it is exothermic reaction, heat is produced, you know that. Consider that heat is product. In endothermic reaction, heat is absorbed. So consider that heat absorbed as reactant. Then you will be able to find out the answer very easily. Why I am saying that for exothermic reaction, the equilibrium constant decreases as the temperature increases. Remember, in this case, I am not saying the equilibrium moves in forward direction or in reverse direction. I am saying equilibrium constant itself decreases as the temperature increases. Understand it. How? Suppose I have a reaction, A and B react and they give you C and D. And this is exothermic reaction. So what I am saying, consider exothermic reaction like this. Heat will be produced in exothermic reaction, means heat is a product. That will increase the temperature. Okay. Now, if you increase the temperature, it means you are increasing the concentration of Q. Understand it like that. If you increase the concentration of D, for example, I ask you, if you increase the concentration of D, in which direction the reaction will go? It will try to reduce the concentration of D, it will go in backward direction. Same is true for Q also. If you increase Q, means by increasing the temperature, the system will try to decrease it, it will go in backward direction. The difference here is that it will actually decrease the equilibrium constant. This is the way you will remember. Opposite will be the case in case of endothermic reaction. In endothermic reaction, heat is absorbed, so heat is on the reactant side. Now if you increase the temperature, you are increasing Q here, system will try to decrease it by going into forward direction, means the equilibrium constant will increase, product concentration will increase permanently. Okay, so that's why the equilibrium constant, which is given by products concentration raised to their stoichiometric coefficient divided by reactants concentration raised to their stoichiometric coefficient. So product concentration will be increased permanently due to increase in temperature. In this case, endothermic reaction, the equilibrium constant will increase. This is what you need to remember. One relationship which you should memorize, okay? You should memorize it for endothermic reaction. For endothermic reaction, memorize so that you don't need to do all these calculations there in exam. Endothermic reaction, the equilibrium constant is proportional to temperature. For exothermic, obviously, it will be inversely proportional. Remember it for endothermic. Endothermic, the equilibrium constant is proportional to temperature. If you increase the temperature, equilibrium constant will increase. How it increases? This is a way for explanation. Now, effect of catalyst, no change. Again, okay, as we talked about in case of inert gas, no change. If volume is not changed, here also no change. And the reason is very simple, because catalyst actually increases the rate of forward and reverse reactions. It does not increase the concentration or decrease the concentration of any one. So the only effect will be that equilibrium will be achieved faster, but it will not affect the equilibrium. Both forward and reverse reactions will be same, only the rate will change. Now the question, for an exothermic reaction, what happens to the equilibrium constant if temperature is increased? If temperature is increased for exothermic reaction, although I have asked you to memorize that for endothermic it is proportional, so obviously for exothermic it will be inversely proportional. So if you increase the temperature, the equilibrium constant will decrease. But how? If you want to recall, A plus B gives you C plus D, and it is exothermic. Heat will be produced. So if you increase the temperature, increase the heat, it will go in backward direction. That's what you will write. In exothermic reaction, with increase of temperature, rate of reaction in reverse direction increases more than rate of reaction in forward direction. It is not reverse here, it will be forward direction. So reaction goes in, or equilibrium shifts in reverse direction. Hence K decreases. Okay, K decreases. Remember, whenever you change the temperature, equilibrium constant will change. Next, the equilibrium constant of a reaction is 2 into 10 power minus 3 at 25 degrees Celsius and 2 into 10 power minus 2 at 50 degrees Celsius. Is the reaction endothermic or exothermic? The only thing you need to identify here, when we are increasing the temperature from 25 to 50, whether equilibrium constant is increasing or decreasing. If with increase in the temperature, equilibrium constant increases, it is endothermic. Otherwise, it is exothermic. Okay. So at 25 degrees Celsius, we have 2 into 10 to the power minus 3. At 50 degrees Celsius, equilibrium constant is 2 into 10 to the power minus 2. 2 into 10 power minus 3 is 0.002. 2 into 10 power minus 2 is 0.02. It means if we increase the temperature, equilibrium constant also increases. It means it is endothermic reaction, directly proportional endothermic reaction. Okay, endothermic reaction. Next, what does the equilibrium constant K less than 1 indicate? K less than 1 indicates, remember, if K is less than 10 to the power minus 3, I have told you, then reaction hardly proceeds in forward direction. Okay, here also you will say that barely proceeds in forward direction, means the reactant's concentration is greater than product's concentration, because K is something product's concentration raised to their stoichiometric coefficient divided by reactant's concentration raised to their stoichiometric coefficient. If this value is less than 1, it means reactant's concentration is greater than product's concentration. So what you will write? You will say the reaction does not proceed much in forward direction, and the reason is very simple. The reactant's concentration is greater than product's concentration. It will proceed, but not much. Next question, for the reaction hydrogen and iodine combined to give you hydrogen iodide, if initially 25 milliliters of hydrogen and 20 milliliter of iodine are present in a container and at equilibrium 30 milliliter of HI is formed, then calculate equilibrium constant. This is something mole concept we have used, similar one. We have done these type of questions. You will write the reaction H2I2 to HI. Initially you have 25 ml of H2 and 20 ml of iodine. Now remember, when all of these are gases, the volumes can be in the same ratio as the moles, because 22.4 liters at STP, if I talk about STP, it will be equal to 1 liter. Okay, no, sorry, 1 mole. These many liters will be equal to 1 mole. So 25 milliliters will be equal to some moles, but the ratio will be, the factor of proportionality will always be same. Okay, so the volumes can be considered as molar ratio, because the ratio of volumes and moles will be same if we have gaseous environment, all gaseous reactants and all gaseous products. So what we will say, initially we have hydrogen as 25 milliliter, iodine as 20 milliliter. So treat these as number of moles and do the same thing what we have done earlier also. Then suppose there is a change, some change, X milliliters used here, the ratio is 1:1:2. So X moles consumed here, same moles will be consumed here of I2, because here the number of moles 1, number of moles 1. The ratio is 1:1. But twice the moles are produced here, so 2X will be produced here. So at equilibrium, what will be the concentrations? We initially had 25, X consumed, so it will be 25 minus X. We had 20 milliliter of I2, X consumed, 20 minus X. We initially didn't have any moles of HI, 2X produced, so it will be 2X only. So at equilibrium, now we know that these are the concentrations. These concentrations obviously are in terms of volume. So according to question, at equilibrium, the hydrogen iodide produced is 30 ml. I'm going back just to show you the question. 30 ml. So in a reaction, initially 25 milliliter of hydrogen, 20 milliliter of iodine, but at equilibrium we have 30 milliliter of hydrogen iodide produced. So it means 2X is 30. We get the value of X from here, substitute those values here to get the concentration of hydrogen and iodine, also means the volumes. So we get hydrogen as 25 minus X, iodine as 20 minus X, 10 milliliter and 5 milliliter. So we have all the values now here. Now go back, what is asked here in the question. Calculate equilibrium constant. You can calculate the equilibrium constant now. Substitute the values. You have found 30 for HI, 10 for H2, 5 for I2. Get the answer. It will be 18. Equilibrium constant will be 18. Next question. What happens to the equilibrium for this reaction if nitrogen gas is added to it at constant volume at constant pressure? And this is something I told you earlier, that when the pressure is constant, then I will explain it later on with an example. Okay, at constant volume also, at constant pressure also. So the state of equilibrium remains unaffected. This is something we have talked about. Why? Because if we add the inert gas, volume has not changed, volume does not change. So number of moles divided by volume, that is concentration, will remain same. Concentration is what? Concentration is number of moles divided by volume. So if we have constant volume, nothing is changing. Okay, remember we are talking about, we insert the inert gas or any non-reacting gas. Nitrogen is not inert gas, it is non-reacting gas here, so it will not affect the reaction itself. So no change in constant volume. But suppose we have constant pressure, it means if initially, try to understand, if initially, for simplicity I am taking the volume V and 2V. Initially the volume is V and we inject nitrogen into it. Initially we had some PCl5, some PCl3, some Cl2. Okay. Now we have nitrogen also into it. We have PCl5, PCl3, Cl2 and N2 also, and volume becomes 2V to maintain the same pressure. Pressure is same, volume increased to maintain the same pressure. Then what will happen in this case? Now consider the concentrations of all three here and concentration of all three here. When you increased the volume, the moment you increase the volume, we can calculate QC there. So try to understand what is Kc. Kc will be product concentration, that is PCl3 concentration, Cl2 concentration divided by PCl5 concentration. And here it will be QC. Obviously later on it will achieve the equilibrium, but the moment you change, the equilibrium will get disturbed. So in that case, what will be the case? Whatever the concentration here was, it was say number of moles of PCl5 N1. So it was N1 by V. For PCl3 if it is N2, N2 by V. For Cl2 it was N3 by V. So I'm writing it here just, okay. Here N1 by V, N2 by V, N3 by V. This is the concentration. But when you have this condition, the concentration of PCl5 now will be N2 by 2, N1 by 2V, N2 by 2V, N3 by 2V. Number of moles at that point of time when you injected nitrogen were exactly same. Then they will change, okay. Equilibrium will get disturbed and it will attain new equilibrium. But the moment you changed, these were the concentration. You will use QC, okay. Now, and QC will be concentrations of products divided by reactants raised to their stoichiometric coefficient again. So this is what? This is initial concentration, whatever the concentration was earlier, half of that, okay. So it is half of PCl3 concentration. This is also half of Cl2 concentration. Sorry, this one and this one, these two, PCl3 and Cl2. This is also half. So everything is half. So I'm saying half of PCl5 concentration. This is PCl5 concentration. So half of this is PCl3 concentration. This is Cl2 concentration. So in each case, it is now half. So QC will be actually equal to this half and this half got cancelled. It will be half of PCl3 concentration, Cl2 concentration and PCl5 concentration. Means QC is half of Kc. It means QC is less than Kc. If QC is less than Kc, the reaction will go in forward direction. You know that. So in this case, when it is constant pressure, you have to apply the simple normal logic. QC is less than Kc or QC is greater than Kc by calculating the new concentrations. New concentrations. Anything not clear? Next. Kp is given 0.04 atm at 899 Kelvin for the equilibrium shown below, that is C2H6 gets dissociated into C2H4 and H2. What is the equilibrium concentration of C2H6 when it is placed in a flask at 4 atm pressure and allowed to achieve equilibrium? It means it is given you have 4 atm initial pressure, and initial pressure will be just by C2H6. It is written when it is placed, this C2H6 is placed in a flask and then allowed to achieve equilibrium. So initially we have 4 atm pressure. Obviously we won't have any amount of ethene and hydrogen, so in that case 0 partial pressure. Then suppose P got consumed here, ratio is 1:1:1. You have 1 mole here, 1 mole here, 1 mole here, so ratio is 1:1:1, means if P is consumed, P will be produced, P will be produced. So equilibrium concentration here will be 4 minus P. Here it will be P because it was earlier 0, P. Here also P. With this value you can write Kp for this reaction. Substitute the values. Kp will be partial pressure of products raised to their stoichiometric coefficient divided by partial pressure of reactant. When you substitute these values, you will get quadratic equation in P, which you can solve. You will take only the positive value. Partial pressure cannot be negative. Okay, so only positive one you will consider. So it will give you 0.38 atm. You will neglect the negative value. Hence at equilibrium, so partial pressure you got. So at equilibrium, you get the concentration of C2H6 as 4 minus P. Why? Because from here you know it is 4 minus P at equilibrium. This is P, this is P. Okay, so you know the partial pressure at equilibrium now. At equilibrium, partial pressure of C2H6 is 4 minus P, that is 3.62. That is asked in the question. That is the answer. What is the equilibrium pressure of C2H6? Next question, calculate delta G naught and the equilibrium constant for the formation of NO2 from NO and O2 as per this reaction, and some values are given, Gibbs energy values are given. So when you calculate delta G naught, the formula we have already talked about in thermodynamics, that delta G naught is given by the sum of all values of delta G naught formation of products multiplied by their stoichiometric coefficients minus sum of all delta G naught of formation of reactants multiplied by their respective stoichiometric coefficients. So we will apply this formula to get the value of delta G naught. After that, we need to find the equilibrium constant also of this reaction. Okay, so if we have delta G naught, we can use the formula delta G naught equals to minus 2.303 RT log K, if you remember that. Okay, so first we will calculate delta G naught by using this formula. Once we get delta G naught, and obviously remember when we do this stoichiometric coefficient, you should remember to multiply by the stoichiometric coefficient. In this case, it won't affect if you don't multiply it by 1/2 here, because the reason is it is 0. For oxygen, standard Gibbs energy of formation will be 0. So you, even if it is MCQ question, obviously it won't matter, but in steps you have to mention half. So when you simplify it, you will get delta G naught as minus 35 kilojoules per mole. One important point about units also, here the values are given in kilojoules, so you will mention the answer in kilojoules. Okay. Now you will apply the formula delta G naught equals to minus 2.303 RT log K. Substitute the value of delta G naught R and T. Delta G naught you have obtained minus 35. And one important point here, because delta G naught you calculated in kilojoules and here you have to use in joules, you will multiply it by 10 to the power 3. Again, common mistake done by students. If you don't convert this into joules, then you need to use here 8.314 into 10 power minus 3. Either way, you effectively have 10 power 3 in the numerator. When you solve this, you will get the value of log K as 6.314. This one will be given, anti-log of 6.314 will be given to you, or log tables, anti-log tables will be given to you, and you will get K as anti-log of 6.314, 1.362 into 10 power 6.